Every second, somewhere in the deep cosmos, a galaxy slips beyond an invisible threshold and vanishes from our observable future. Light from more than 2 trillion galaxies races across the void toward Earth, yet most of that ancient radiation will never complete its journey. We exist within a sphere stretching nearly 62 billion light-years in every direction, surrounded by an edge forming and shifting in real time. Beyond this boundary lies infinity itself, endless and fundamentally unknowable. The universe presents us with a paradox that defies intuition. Space extends forever in all directions, infinite and without physical boundaries. Yet each observer stands at the center of a measurable sphere with definable edges. Both statements hold true simultaneously, creating one of the most profound puzzles in cosmology. If you ask whether the cosmos has an edge, physics answers no. Space continues outward without walls, without borders, without any cosmic barrier marking where reality terminates. Galaxies exist beyond galaxies, structures beyond structures, extending into distances so vast that numbers lose meaning. But here lies the twist. You cannot see all of it. You cannot reach all of it. You cannot even receive light from most of it. Despite inhabiting an infinite cosmos, you remain trapped inside an observable bubble. This bubble possesses measurable boundaries and real limits, and those limits contract around you with each passing moment. The edge consists not of matter or energy. Nothing physical obstructs your view. Instead, the boundary emerges from something far more fundamental. Time itself creates your cosmic prison. Light travels at exactly one speed through empty space, approximately 186,000 miles per second. Nothing moves faster. This cosmic speed limit has remained constant since the universe began roughly 13.8 billion years ago. Combine these facts, and you encounter a wall. Light from distant regions has been racing toward Earth since the beginning of time, but much of it has not yet arrived. Some light will reach us tomorrow. Some will arrive in 1 billion years. But vast stretches of space sit so distant that their light will never complete the journey. This unreachable distance defines your cosmic horizon. Scientists call this boundary the edge of the observable universe, the only region you can possibly detect or interact with. Everything beyond remains forever hidden, separated not by distance alone, but by the fundamental structure of spacetime itself. You could construct a spacecraft capable of traveling at light speed, aim it toward that horizon, and accelerate for eternity. You would never reach the boundary. The edge would recede faster than you could approach, always maintaining the same relative distance. The situation grows stranger still. Your cosmic horizon differs from every other observer's horizon. An observer in the Andromeda galaxy sees a different sphere centered on their location. Parts of their observable universe overlap with yours, but vast regions they perceive remain invisible to you forever. Every point in space possesses its own cosmic horizon, its own bubble, its own edge. Infinity contains countless edges, each one real, each one unique. We inhabit a universe that is simultaneously boundless and bounded, eternal and limited, infinite and trapped. You occupy the exact center of the observable universe. Stand anywhere on Earth, anywhere in the galaxy, anywhere in the cosmos, and the same rule applies. You sit at the middle of a sphere, extending equally in all directions. Move one step and your sphere moves with you. Travel 1 million light-years and nothing changes. The bubble follows you perfectly, always centered, always the same size. This is not an illusion or trick of perspective. This represents fundamental cosmic geometry. Picture yourself standing in an enormous dark warehouse with a single flashlight. The beam illuminates a circle around you, creating a boundary between what you can see and what remains in darkness. Walk forward, and the circle moves. The illuminated area never changes shape or size, but different parts of the warehouse come into view while others fade behind you. Your cosmic horizon operates exactly this way, except the flashlight is time itself and the warehouse is infinite. Every observer in the universe experiences the same phenomenon. An alien civilization 3 billion light-years away sees their own sphere, their own horizon, their own observable universe. Some galaxies they detect exist beyond your reach, invisible to you forever. Meanwhile, you observe galaxies that remain eternally hidden from them. The cosmos reveals itself differently to every observer, granting each one a unique window into infinity. No observer can see the entire universe. No location offers a complete view. Even if you could survey every galaxy in your observable region, catalog every star, map every structure, you would still have examined only an infinitesimal fraction of what exists. The full universe extends far beyond what any single observer can detect. Infinity ensures that everyone perceives merely a sample, a cosmic preview, never the whole show. Your observable universe measures roughly 92 billion light-years across. That distance contains approximately 2 trillion galaxies, each hosting hundreds of billions of stars. The numbers become incomprehensible quickly. Yet this entire region, this vast cosmic domain, represents only a minuscule portion of total existence. If the universe is truly infinite, then your observable sphere is infinitely smaller than the whole. Your bubble contains everything you can ever see, measure, or interact with. Every photon striking your eye or telescope originates from within this sphere. Every scientific discovery, every astronomical observation, every piece of cosmic data comes from inside these boundaries. Light deceives you constantly about distance. Look at a galaxy 13 billion light-years away and you see light that departed 13 billion years ago. Simple mathematics suggests that galaxy sat 13 billion light-years from Earth when it released those photons. This is incorrect. The galaxy was actually much closer when the light began its journey. By the time those photons reach your telescope, that same galaxy now sits far beyond 13 billion light-years. The light traveled through expanding space, and space itself betrayed the measurement. This deception reveals something profound about cosmic distance. When astronomers report distances to remote objects, they often use light travel time. They measure how long light spent crossing space. A galaxy whose light took 10 billion years to arrive gets labeled as 10 billion light-years away. But that number tells you only when the light departed, not where the galaxy currently resides. Space expanded during the journey. The galaxy drifted farther away while its light approached you. The current distance exceeds the light travel distance by enormous amounts. Consider the most distant galaxies visible today. Their light has been traveling for over 13 billion years, almost the entire age of the universe. Simple calculations suggest they sit roughly 13 billion light-years away. Reality tells a different story. Those galaxies currently exist more than 46 billion light-years from Earth. The expansion of space during the light's journey stretched the distance by more than a factor of 3. The galaxies moved while their light was in transit. Now imagine attempting to reach one of those galaxies. You construct a spacecraft capable of traveling at light speed. You aim it toward a galaxy whose light took 12 billion years to reach Earth. You might think the journey would require 12 billion years. You would be catastrophically wrong. That galaxy has been receding the entire time its light traveled toward you. The current distance exceeds 30 billion light-years. Even moving at light speed, you could never catch it. The space between you and that galaxy expands faster than you can close the gap. Distance becomes fundamentally ambiguous in an expanding universe. Two galaxies can sit far enough apart that the space between them expands faster than light travels. They drift apart at speeds exceeding the cosmic speed limit. Yet neither galaxy moves through space faster than light. They remain stationary in their local space. The space itself stretches, carrying them apart. The expansion of the universe does not obey the same rules as motion through space. This creates regions you can see but never reach. Galaxies beyond a certain distance, currently about 16 billion light-years away, are crossing an invisible threshold. Light leaving them today will never arrive at Earth. The space between us and them expands too rapidly. Space itself grows larger every second. Forget the image of galaxies flying through empty void like bullets through air. That picture misleads completely. Galaxies mostly remain in place. The space between them expands, creating new distance where none existed before. Imagine bread dough with raisins mixed throughout. As the dough rises, the raisins move apart, but each raisin remains stationary relative to the dough around it. The dough itself grows, carrying the raisins along. The universe behaves like that dough, except the dough is spacetime itself. This expansion has no center and no edge. Every point in space expands equally. An observer in any galaxy would see all other galaxies receding, creating the illusion they occupy the center of expansion. But no true center exists. The universe expands everywhere simultaneously, stretching the fabric of space-time uniformly in all directions. Space does not expand into anything. There is no outside container. The universe is all there is. Measuring this expansion reveals something unexpected. Nearby galaxies recede slowly. Distant galaxies recede faster. Double the distance, and you double the recession speed. A galaxy 1 million light-years away might drift from us at 14 miles per second. A galaxy 2 million light-years away drifts at 28 miles per second. This relationship holds across the observable universe. The farther away something sits, the faster it recedes. Push this pattern to its limit. At some distance, galaxies recede at exactly the speed of light. This distance currently measures about 14 billion light-years. Beyond that boundary, galaxies recede even faster. Some race away at twice light speed, others at 10 times. The most distant observable galaxies recede at roughly 3 times the speed of light. They violate no physical laws because they are not moving through space. Space itself carries them. This creates bizarre consequences. Light from these ultra-distant galaxies travels toward Earth at light speed, the fastest anything can move. Yet the galaxies themselves race away faster than light. The photons make progress toward us, but they fight against an expanding river of space. Imagine swimming upstream in a current flowing faster than you can swim. You move forward through the water, but the water carries you backward faster. You make negative progress toward shore. Light from distant galaxies experiences exactly this. Photons from a galaxy receding at twice light speed travel toward us at light speed, but space expansion carries them backward at twice light speed. The net result is they actually move away from us at light speed. The light loses ground despite traveling at maximum velocity. But early in cosmic history, the expansion rate was slower. Back then, even though that galaxy receded faster than light, its light could make forward progress. The photons gradually closed the distance. Eventually, they entered regions where expansion had slowed enough for them to reach us. We can see galaxies that always receded faster than light. Their light reached us anyway by starting the journey when expansion was slower and gradually entering regions where they could make progress. The observable universe contains countless galaxies that never, at any point in their history, receded slower than light relative to us, yet we can see them clearly. The rules governing cosmic visibility defy simple intuition. The sphere surrounding you measures 92 billion light-years across. That boundary marks the farthest distance from which light could have possibly reached Earth since the universe began. Anything beyond that distance remains invisible, not because instruments lack power, but because insufficient time has passed for light to complete the journey. The universe is 13.8 billion years old. Light traveling at constant speed for that entire duration covers a certain distance. But space expanded while the light traveled, stretching the journey and placing the source much farther away than 13.8 billion light-years. Current calculations place your horizon at 46 billion light-years in every direction. Double that distance and you obtain the diameter, 92 billion light-years from edge to edge. This sphere contains everything you can possibly observe. Every photon ever detected by human instruments originated from inside this boundary. Every star, every galaxy, every quasar, every cosmic structure visible to telescopes sits within this cosmic sphere. Beyond the wall lies infinity, forever inaccessible. The oldest light you can detect is not visible light at all. It arrives as microwaves, ancient radiation stretched by expansion into long wavelengths. This radiation fills the entire sky, emanating from all directions equally. It represents light released when the universe was just 380,000 years old, currently about 46 billion light-years away from us today. That shell of ancient light marks the practical edge of observation. Beyond that shell, the universe was opaque. You cannot see farther because light could not travel freely through the early cosmos. Matter was too hot, too dense, too ionized. Photons scattered constantly off free electrons, unable to travel in straight lines. Only after the universe cooled enough for atoms to form did light finally break free. That moment of liberation created the shell of radiation you detect today. Anything that happened before that moment remains hidden behind an impenetrable curtain. This creates a nested set of boundaries. The theoretical limit at 46 billion light-years represents how far light could travel in principle. The practical limit sits at roughly the same distance but represents the moment the universe became transparent. Between you and that wall lie all 2 trillion galaxies of the observable universe, arranged in an intricate cosmic web of filaments and voids. Beyond the wall lies the unobservable universe, potentially infinite in extent. A second boundary exists much closer than the first. Currently sitting at about 16 billion light-years away, this boundary separates regions you can see from regions you can influence. Galaxies beyond this closer boundary are crossing a threshold. Even if you sent a light-speed signal toward them right now, that signal would never arrive. Space expands too quickly. The message would drift farther from its target forever, making progress through space but losing ground to expansion. You can see these galaxies, but you can never contact them. They exist in your observable universe, but outside your reachable universe. You can watch their past unfold, study their properties, measure their light, but you cannot send them information. You cannot visit them. You cannot interact with them in any way. They are observationally present but causally disconnected, visible ghosts beyond the point of contact. This second boundary shrinks with every passing moment. More galaxies cross it constantly, slipping beyond reach forever. Galaxies at the edge of the observable universe recede at 3.3 times the speed of light. The speed of light represents the ultimate cosmic speed limit. Nothing can travel faster. Yet galaxies routinely exceed this limit by factors of 2, 3, or more. They violate no laws of physics. They break no rules. The cosmos allows this because the rule about light speed applies to motion through space, not to the expansion of space itself. Special relativity sets the speed limit for objects moving through spacetime. A rocket cannot accelerate to light speed. A particle cannot outrace photons. All motion through space obeys this absolute restriction. But the expansion of the universe involves something different. Space itself grows larger, and that growth has no speed limit. The fabric of spacetime can stretch as fast as conditions allow. Distant galaxies carried along by this expansion can recede from each other at any speed whatsoever. Picture 2 galaxies separated by enormous distance. The space between them expands everywhere simultaneously. Near Earth, a small amount of new space appears every second. Near the distant galaxy, another small amount appears. All along the path connecting them, space expands at the same rate. Add up all these small expansions across millions or billions of light-years, and the total distance grows faster than light can travel. Neither galaxy moves through space faster than light, but the space carrying them expands without limit. This creates a strange consequence for light traveling between them. Photons from ultra-distant galaxies fight against expansion. They race toward Earth at maximum speed, but space carries them backward faster than they advance forward. Early in the universe's history, when expansion was slower, these photons could make progress. They gradually closed the distance, despite swimming upstream against expansion. Eventually, they entered regions where local expansion had slowed enough for them to reach us. We see them now as ancient redshifted light from near the cosmic horizon, but photons emitted from those same galaxies today will never arrive. The current expansion rate exceeds the rate when that ancient light was emitted. Modern photons face a stronger current. They cannot make progress against it. They will drift away from Earth forever despite traveling at light speed toward us. The galaxy that emitted them recedes faster than its own light can approach us. This defines the event horizon, the boundary separating galaxies we can still communicate with from galaxies forever beyond reach. Every second, approximately 20,000 galaxies cross this threshold. They slip beyond the event horizon, entering the unreachable realm. You can still see them because their old light continues arriving. But light they emit today, tomorrow, or any time in the future will never complete the journey. You are watching the last visible moments of these galaxies, frozen in time as they cross into cosmic isolation. Over billions of years, they will fade from view completely as their final photons arrive and no new ones follow. The event horizon currently sits about 16 billion light-years away. That makes it much closer than the observable horizon at 46 billion light-years. You can see galaxies far beyond the event horizon because their past light made the journey when conditions were different. But those distant galaxies are already unreachable. They crossed the event horizon long ago. Their current state, their present condition, their modern evolution remain forever hidden from view. 380,000 years after the universe began, something changed forever. Before that moment, the cosmos was a roaring furnace of naked particles. Electrons drifted free, unbound to atomic nuclei. Photons scattered constantly off these free electrons, bouncing from particle to particle like pinballs in a machine. Light could not travel in straight lines. The universe was opaque, a thick plasma fog impenetrable to electromagnetic radiation. Temperature determined everything. When matter exceeds roughly 5,000 degrees, electrons tear free from atoms. The electromagnetic force binding them breaks down. Protons and electrons drift separately, creating a plasma where charged particles swarm everywhere. Light interacts strongly with free electrons, constantly scattering and redirecting. This creates opacity. Lower the temperature below 5,000 degrees and electrons recombine with nuclei. Atoms form, free electrons disappear. Suddenly, light can travel unimpeded across cosmic distances. This transition happened across the entire universe almost simultaneously. As expansion cooled the cosmos, conditions reached the critical temperature. Electrons combined with protons and helium nuclei. Within about 100,000 years, the universe transformed from opaque to transparent. All the light that had been trapped, scattered endlessly by free electrons, suddenly broke free. It streamed outward in every direction, carrying information about conditions at that moment. That light has been traveling toward you ever since. Stretched by expansion, red shifted from visible light into microwaves. It fills the sky today as a faint glow called the cosmic microwave background. Every direction you look, you detect this ancient radiation. It represents light released from a spherical shell surrounding you, currently sitting about 46 billion light-years away. That shell marks the surface of last scattering, the moment when photons last interacted with matter before beginning their long journey to Earth. This shell is the farthest thing you can see with light. Beyond it, the universe was opaque. Light could not travel freely. You might imagine looking farther back with powerful enough telescopes, but no telescope can pierce the plasma curtain. It represents an absolute barrier to electromagnetic observation. Everything that happened before atoms formed remains hidden behind this wall of scattered light. The cosmic microwave background itself reveals extraordinary detail. Temperature variations across the sky show tiny fluctuations in density, the seeds of all future cosmic structure. These variations measure about 1 part in 100,000. Regions slightly denser than average would eventually collapse under gravity to form galaxies. Regions slightly less dense would become the voids between galaxy clusters. The entire large-scale structure of today's universe traces back to these microscopic fluctuations visible in the ancient light. Looking at the cosmic microwave background means observing the oldest possible image of the universe. It represents baby pictures of the cosmos taken when everything was simpler, smoother, more uniform. Since that moment, gravity has amplified the small variations into the magnificent complexity visible today. The cosmic microwave background confirms the universe had no center even then. Scientists hope to see farther back using other signals. Gravitational waves and neutrinos can pass through the plasma that trapped light. These particles could carry information from even earlier moments, potentially from the first second after the universe began. Future detectors might pierce the plasma curtain using these alternative messengers. But for now, the cosmic microwave background marks the limit of what you can see. This radiation began its journey 13.8 billion years ago. Well, almost. The universe was 380,000 years old when this light was released, making the radiation 13.79962 billion years old. That tiny difference matters because it reveals something crucial. The universe had already expanded significantly before light could travel freely. The cosmic microwave background emanates from a shell of space that was much closer to Earth when the light was emitted. Current distance to that shell measures about 46 billion light-years. But when the radiation departed, the entire observable universe was just 42 million light-years across. Expansion has stretched everything by a factor of roughly 1,100 since then. The light itself has stretched by the same amount. Photons that left as visible or ultraviolet light now arrive as microwaves with wavelengths about 1 millimeter long. This stretching reveals the expansion history of the universe. Temperature tells the same story. When the cosmic microwave background was released, the universe blazed at about 5,400 degrees, hot enough to glow orange-red. Today, that radiation measures just 2.7 degrees above absolute zero, colder than the vacuum of space. Temperature varies slightly across the sky. One direction might measure 2.726 degrees, while another measures 2.724 degrees. These tiny variations, measured in millionths of a degree, reveal the structure of the early universe. Hotter spots represent regions slightly denser than average. Cooler spots show regions slightly less dense. Gravity has been amplifying these variations for 13.8 billion years, transforming them into the galaxies and cosmic voids we see today. The cosmic microwave background also reveals the geometry of space itself. Hot and cold spots appear at specific angular sizes across the sky, measuring about 1 degree across. This size depends on the curvature of space. If the universe curved like a sphere, the spots would appear larger. If it curved like a saddle, they would appear smaller. Observations show the spots match predictions for flat space almost perfectly. The universe appears to have exactly zero curvature within measurement error. This flatness reveals something extraordinary about cosmic density. For space to be flat, the universe must contain a precise amount of matter and energy. Too much in space curves inward, like a sphere. Too little, and it curves outward like a saddle. The measured density sits right at the critical value, balanced on a knife edge. This suggests either remarkable cosmic coincidence or some underlying principle that forced the universe to flatness. Your universe has two edges, and they tell different stories about time. The first edge, the particle horizon, defines how far light could have traveled since the universe began. It represents the past, marking the boundary of everything whose light has had time to reach you. Currently sitting about 46 billion light-years away, this horizon expands constantly as the universe ages. Every second that passes, light from more distant regions completes its journey and enters your observable sphere. The second edge, the event horizon, defines something stranger. This boundary marks the farthest distance from which light emitted right now could ever reach you in the future. It represents a division between galaxies you can still contact and galaxies forever beyond reach. Currently sitting about 16 billion light-years away, this horizon is much closer than the particle horizon. But the event horizon is not expanding. In a universe dominated by dark energy, it actually shrinks. These two horizons move in opposite directions. As time passes, the particle horizon expands outward. You see light from more distant regions that released it long ago. Meanwhile, the event horizon contracts inward. Fewer galaxies remain contactable with each passing moment. Eventually, billions of years from now, the two horizons will converge. The particle horizon will reach its maximum size, while the event horizon shrinks to a minimum. Picture what this means for cosmic observation. Right now, you can see galaxies whose light has been traveling for over 13 billion years. These galaxies sit more than 30 billion light-years away due to expansion. Their ancient light shows them as they were in the early universe, young and actively forming stars. But these same galaxies crossed the event horizon long ago. Light they emit today will never reach Earth. You are watching a delayed broadcast of their past, but their present remains forever unknowable. Thousands of galaxies cross the event horizon every single day. They slip beyond the boundary where communication becomes impossible. You can still see their old light for billions of years to come, but new light from them will never arrive. As their final ancient photons reach Earth, no replacements follow. These galaxies will gradually fade from view. Their images will redshift into invisibility, stretched by expansion, until detecting them requires impossible sensitivity.